Okay, hello and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and serving the over 100,000 computing professionals and students who are ACM members. My name is Eric Simon. I am currently a chief architect at SAP in the area of information management. In the past, I was the engineering lead for data access and data federation within SAP Business Object product. I was also previously CEO of Medians, a French startup company developing data federation technology, and a senior research scientist at INRIA in France, which is one of the largest European research centers in computer science. My research interests cover different areas of database, like database system design, database languages, query optimization, and data integration methods and algorithms. So I will be your moderator today. And let me move now to a couple of information regarding ACM. As you know, ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in the constantly changing world of computing with a range of ACM Learning Center resources at the org URL that you see. You can see some of the highlights on your screen already. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in the global environment, and in particular, ACM provides timely computing information published by ACM, like CSEM or Q magazines, access to the ACM digital libraries, and international conferences that draw leading experts on a broad spectrum of computing topics, support for education, research, etc. ACM enables its members to solve critical problems using new technology that enriches our lives and advances our society in the digital age. So let me move now to the housekeeping slide. Before we get started, I just want to mention a few housekeeping items that are shown on the slide in front of you. On the top right corner of the slide area on your screen, there is a button that will allow you to enlarge the slides. You may also enlarge the slides at any time by dragging the corner of the slide window, and the slide will advance automatically through the event. During the presentation, you can minimize the slide area, the Q&A and bio screens using the buttons on the bottom panel. You can also use a number of widgets also found on the bottom panel, including Facebook, Twitter, Wikipedia, and a resource list, where you can get a copy of the slides. If you are experiencing problems with our web interface, you can refresh your console by pressing the F5 key in Windows, or the command +R if you're on a Mac, refresh your browser if you're on a mobile device, or close and relaunch the presentation. You can also visit the webcast help guide by clicking on the Help widget below the slide window. To control the volume, you just have to adjust the master volume on your computer. At the end of the presentation, we will have time for questions, and we do hope you have several questions. If you think of a question during the presentation, you can type it into the Q&A box and click on the Submit button. You do not need to wait until the end of the presentation to begin submitting questions. You may also use the Q&A box to suggest topics for future webinars. At the end of the presentation, you'll see a survey open in your browser. Please take a minute to fill it out to help us improve our webinars. The session will be recorded and archived. You will receive an automatic email notification when it's available, or you can check learning.acm.org in a few days for updates. You can use the Facebook and Twitter widget on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using the hashtag ACM Webinar CS Inventor. We'll be watching for your tweets. And so let's now introduce directly the presentation of today, which is The Changing Nature of Invention in Computer Science by Denis Shasha. Denis Shasha is a professor of computer science at the Courant Institute of New York University and a 2013 fellow of the ACM. In his research, Denis works with biologists on pattern discovery for network inference with computational chemists on algorithms for protein design, with physicists and financial experts on algorithms for time series, on clock computation for DNA computing, and on computational reproducibility. His other areas of interest include database tuning as well as tree and graph matching. Denis has written 5 technical books about database tuning, biological pattern recognition, time series, DNA computing, resampling statistics, and causal inference in molecular networks. He has co-authored over 70 journal papers, 70 conference papers, and 20 patents. Because he likes to type, as he used to say, he has also written 6 puzzle books, a biography, and a book about the future of computing, as well as a puzzle column for various publications, including Scientific American. So Denis, the word is to you, and we look forward to your presentation here today.
Great. Well, thank you very much, Eric, and thank you for attending this. Although I can't see you, my spirit is with you, I hope. So this book is based on, this talk is based on 2 books that I wrote with a journalist, Kathy Lazaire. Now, Kathy is a very smart person, but she's not a computer scientist. And our way of writing these books was for me to formulate the questions, to find the people, but that she conducted the interviews. And as a result, many of the quotes we get are much more folksy, if you will, than they would otherwise be. They're not very technical because Kathy made the interviewee be very clear. So whenever I give direct quotes, the fact that they're so direct and colorful is due to her. So today what I'm going to be talking about is really basically people and how they invent things and why they invent things and how that will change in the course in the future. So I'm going to now advance the slides past all these housekeeping things. And I'm going to start with the first inventor. Okay, so great inventor number 1. So this is a quote from this inventor. So I'll just let you read it. Flunk, in case you're not a native English speaker, it means failed. He never studied, he hated studying, he was goofing around. So if your child were doing this, you might not be so happy. As it happens, the parents of this person were very wealthy, and so they could send him to summer school in New Hampshire, but of course he just went sailing. Now, this person is John Backus, who his first invention was the development of FORTRAN. And let's just look at how he invented things and what was his motivation. So first of all, let's talk a little bit about his life. So he graduates at 25 from Columbia's College of General Studies. Now, it's true that I'm a professor at New York University and we have a certain rivalry, but take that aside, even putting that aside, Columbia's College of General Studies in the late 1940s, probably not so hard to get into. So he went there, he kind of barely passed, he was doing okay, he had no idea what to do. So this is, as I said, the late 1940s. He goes to the IBM building in New York City, gets a tour, thinks, wow, this enormous vacuum tube computer that they have there looks really fascinating. Could I possibly get a job there? And they said, sure, just take a test. And he takes a test and he becomes a programmer. And his job is to figure out orbits of planets and moons around planets. And he loves the physics, but he hates the programming because the programming is in machine language and it's very tedious. And besides, there is no floating point number, so everything's fixed point. You have to remember scale factors. Just very, very difficult. So the first thing he says is, you had to know so much about the problem. It had all these scale factors, and you had to keep these numbers in your head. So you would have to descale numbers and make them smaller so that the multiplications would work out. And so the programming was hard, even though the science wasn't as hard. So now, again, imagine that your child is in this situation, or that you yourself were in that situation. You might have been told by your parents, or you might tell your children, hey, look, just grin and bear it. Just work harder and you'll get it right, and that's how you should do things. But that's not how Backus worked. Backus, he said, no, if it's too hard, I have to invent a way around it. So first he developed a floating point to fixed length compiler. And then he suggested the design of a machine, of a language for the next IBM machine. That language became Fortran. Now, interestingly enough, he had opposition within IBM people who said, well, this could be good, except that computer time is so valuable, programmer time is not. And so if this high-level language is slow, then it's really not going to be worth anything. But he convinced his management that he could make it efficient and that it would make programming get done a lot faster. Now, Backus, of course, gets all the credit, but he had a team, and he gives them all the credit, really. He says designing the language, first of all, was not that hard. Making it run fast was what was hard. And for that, he recruited linguists, mathematicians, logicians. There were no computer scientists at this time. It's the early 1950s. And he described his role as breaking up the chess games that were still going at 2 p.m. Okay, so he had a bunch of smart people and probably people who liked each other. They were working together. They solved problems, and they would get distracted by chess. Terrible, terrible. So Fortran, skipped a slide. Fortran is tremendously popular in industry. Tremendously popular meaning as popular as the machine that IBM was producing at that time, which was a few hundred. But that was tremendous popularity. Academics liked it less, so John McCarthy tried to do math with it, and he found that he needed recursion with no recursion. So McCarthy, of course, went off to invent Lisp, but also the European committees said, well, we need a new programming language that allows recursion and that's kind of nicer than Fortran. And that led to Algol. So Backus was invited to the Algol committee, and he said, well, there would just describe stuff in English. Here's the statement. Here's an example. And then he said, well, you could never really find out what was going on. It was never precise enough. So you needed to learn how to be precise. Now, when we interviewed him, he said that what happened was he figured out a way to do it, but all of the time for comments was gone, and so he had to persuade a nice mailman in Maine to backdate the envelope so that it would look as if his comment had gotten in on time. Anyway, his comment was basically context-free grammars. So context-free grammars had been used by this time, this is now the late 1950s, by Chomsky in linguistics, and Backus came and decided to use them for programming languages. So if you've studied linguistics or if you've followed linguistics, you know that context-free grammars are not sufficient for natural languages, but they're really extremely useful, even if not always sufficient for computer languages. And this all started because Backus was frustrated by these unproductive meetings in the Algol committee. Backus again gives lots of credit to Nauer, who was a mathematician and helped Backus formalize this. Again, it's beautiful work, and as we all know, we use this every day, all the time. So now we've seen two inventions, both born basically of frustration, both born basically of being maybe a little bit angry at the things that are and trying to make them better. So now Backus was at this point an IBM fellow. This is the late 1970s, and Backus is giving his Turing Award lecture. And Backus doesn't just say, oh, look at the wonderful things I did. No, instead he said, look at the terrible thing I did. Well, not really entirely terrible, but it has its problems. And so he looked at his own invention at Fortran, and he says, well, once you've written a Fortran program, you can't tell what's really going on. It multiplies some numbers. There's no way really to understand it. It's very hard to debug it. And so to be able to understand how the program works, it's better to have a side effect-free programming language or programming model, which is functional programming. Now, Backus didn't invent functional programming, nor did he claim to. In fact, he gives a lot of credit to Ken Iverson from APL, but Backus certainly said this is why, and because it came from him who was criticizing his own invention, it got a lot more credibility. So, an example of what Backus was trying to get was he wanted side effect-free functions. He was looking for composition, easy parallelism. Remember, this is the late 1970s. Parallelism was only a boutique kind of concept then, not like now with multi-cores. And the idea is that one thinks of this as basically almost looking at mathematical formula which are side effect free and allow composition. So the Backus style, if you're annoyed, don't grin and bear it. Now, I'm not telling you that you should tell your children just to go play video games, but at the very least, you should say, well, if you don't like it, maybe try to invent a new thing to do. I like the quote of Alan Kay, a little bit of a nod to Marx. The best way to predict the future is to invent it. And of course, Alan Kay also did great things like this. And both Backus and Alan Kay were interviewed in our first book, Out of Their Minds, and it turns out that a lot of the people who we interviewed in that book had this style. They didn't like the way things were, and so they would change things. And also, some of them, like Backus, had this extreme honesty where they would even change what they had invented themselves and criticize their own inventions. That is more rare, I have to say. Okay, let's look at our what makes him tick then. For our second inventor, so for the first inventor it was kind of anger. For our second inventor, outstanding student, no summers in New Hampshire sailing. Outstanding student, extremely strong mathematician and logician, does his master's, does a beautiful thesis in algebra, goes to the Institute for Advanced Studies, becomes a full professor of mathematics where the committee didn't even recognize his work in computer science. Some of his best-known work, non-deterministic finite state automata, which he did with Dana Scott. And if you think about how often you use automata, how often you do string matching, this is just fundamental groundbreaking work. Randomized algorithms. We use these all the time. Every time we need to get large prime numbers. And so that's one of the primary applications and one of the primary developments from randomized algorithms. So if you don't know yet, well, I'll tell you his name in a minute. One more slide of suspense. Okay, so if you think about non-determinism and randomized algorithms, think about how different that is from what computing languages, at least, inspire you to do. Typical operations in the computing languages are imperatives. They're do, assign, end, add, copy. You're commanding the machine to do something. You expect it to do it without question, like some kind of military commander who expects soldiers to do exactly what he or she says. Michael Rabin's work, so okay, I've let the cat out of the bag now, involves giving the machine choice. In one case, allowing the exits from one state to be non-deterministic. In the other case, allowing random dice throwing, essentially, to determine where an algorithm is going to go. Very interesting. So this is Michael Rabin, a little bit younger than now. But here's a small sampling of prizes. I've been to his apartment in Jerusalem, and he's got a whole wall full of prizes. Maybe the most of any computer scientist. It's actually kind of remarkable. So I want to just give you a feeling because, one thing is just hearing history, another thing is actually using your mind. So I'm going to give you a little puzzle. I'm not going to pause too much to answer it. I'm going to give you a small pause so you can think about it. So John McCarthy, besides inventing Lisp and then non-monotonic and logic and for AI and many other things, he was a great puzzle writer. And since I love puzzles, I always appreciate great puzzles. And in 1958, he proposed the following puzzle. Okay, so there are two countries in a state of war. one country is sending spies into the other country. Remember, 1958 is the middle of the Cold War. Okay, so one country is sending spies into the other country. The spies do their spying, and then they come back, but they're in danger of being shot by their own guards as they try to cross the border. Okay, sounds bad. So what do? They need some kind of password mechanism so that when they come back, the guards don't shoot them. But there's a little hitch. So the spy might go in one way and come back another way, so we can't count on just the guard recognizing the spy. So you want a password mechanism. The assumption is that the spies are high caliber people, they're ACM computing society members, and they can keep a secret. But the border guards, well, they kind of have a good time. They like to have a good time. So they go to the local bars, they chat, and so basically whatever you tell them will be known to the enemy. So that's the issue. So now you have to tell the guards something, but know that whatever you tell them will get to the enemy. So the question is, can you devise an arrangement by which the spy will be able to come safely through, but the enemy will not be able to introduce its own spies by using the information that the guards have? So at first glance, this seems very difficult. Like if you tell the spy, well, just say abracadabra or something, but now you're telling that to the guard. Now the guard tells the local temptresses in the bar, and now that goes across the border. Now enemy spies can come in and say abracadabra. So that wouldn't work. So what Rabin did was he made use of the following procedure that von Neumann had suggested to generate pseudo-random numbers. So let me just tell you what this procedure is. Procedure goes like this. Let's say you have a number. I'm just doing a small number. So you have a number, x is 341. You square it, and then you take the middle 3 digits. Well, of course, the middle here is a little bit difficult because there are only 6 digits, but let's just take 162. So you can see that those are digits inside that larger number. And that becomes the next number. So for the pseudo-random number generator, 341 would be the first number, 162 would be the second number, then you would square 162, again take the middle digits, and that would be the third number, and so on. So Rabin observed that, well, it's very easy to go from x to y. All you have to do is square a number and then take out some middle digits. One could even do that in the mechanical calculators of the late 1950s. But going from y to x, well, that's a completely different thing. If I know that the middle digits of the square of a number are 162, it's very hard to guess that 341 would be the number that would generate that. So that's your big hint. So I'm going to give you like 10 seconds to think about that. So how would you use that to solve the spy versus spy problem? Okay, sorry, I can only give you 10 minutes. When I give this live, then I can actually ask for people, but it's hard to see hands being raised. And I can't throw you a Kit Kat, which is what I would normally do if you answer the question correctly. Anyway, so the idea is that, and I guess I don't have the solution there. Okay, the idea is that you give the guard Y. And then when the spy comes, the spy tells the guard X. The guard then does the squaring, takes the middle digits, hopefully is not too drunk to see that the middle digits are in fact Y, and then the spy gets to go through. But even if the guard gives away 162, and even if the guard tells the people in the bar 162, it's still very hard to figure out the 341, which is what an enemy spy would need to get in. So of course, this is not applicable if there are only 6 digits, but if there were hundreds of digits, this would be a good approach. Now, so the implication of this is that difficulty can be useful to share secrets. And so the whole notion of complexity came from this puzzle, basically. And Rabin would when he would give talks, he would say, look, there's more to computer science than just showing computability. It's also a question of showing, that is decidability, there's also the question of showing feasibility. And so entire notions of time complexity, were partly due to his solving this puzzle and the implications of how to solve such a puzzle. So if we contrast the Rabin style with the Backus style, Rabin would find, usually through discussion, still does, usually through discussion, simple to understand problems that others consider too difficult to solve. So he's amazing about taking discussion. So he'll go visit someplace and people will talk to him and then he'll figure out something cool to do. And the other hallmark of this work is that the algorithms are often quite simple and efficient to implement, which I find remarkable, because you start with a problem that other people might not even know how to solve, and then you end up with an algorithm that's simple. That's just a thing of beauty. We actually work together on a problem to prevent software piracy. I'm not going to stick my hand in that beehive, but anyway, the upshot of that work was that we could figure out how to prevent piracy without infringing on privacy. And that also, many times we would take walks together and we would find some analogy from a movie, and then that would help our algorithm. So it was very freewheeling, analogy-driven kind of approach. So far we've seen inventors that use clever design, and then the computers are later put to work. So you do things on paper, you figure out algorithms, and then the computer does its thing. And really, in a way, that's the major tradition of engineering. You have ever-increasing precision and control. So if we look, for example, at this beautiful watch, it's an example of beautiful, beautiful controlled engineering. Lots of little gears, gears perfectly fit. You have complete control over the environment, and therefore you can deliver an extremely high-quality product. But now, what about new environments? What about spacecraft? Okay, so now spacecraft, if you think about it, they're bombarded by particles. Everything could go wrong. To quote Don Rumsfeld, whether he's famous or infamous, there are known unknowns, there are unknown unknowns. So who knows? Maybe there are aliens that are messing with your spacecraft. So you don't even know what could go wrong. So it's completely the opposite environment from the Seiko watch. So you can't anticipate everything, and you have to be prepared to adapt. So here we have a little picture of a spacecraft, another of a rover. So what do you do when the spacecraft goes wrong? So the first thing you might do, and what's really done mostly in practice now, is the spacecraft calls home. And it says, hey, help, I'm in trouble. And so like a small kid who scrapes his knees while playing with Billy and goes home. But of course the spacecraft can't go home, it can only call home. And who do they call, at least if it's NASA? They call the Jet Propulsion Laboratory, which I didn't realize this until I saw this picture, is in a volcanic crater, which I think is so cool. And in particular, they're quite likely to call this person, whose name is Glenn Reeves. Now, Glenn Reeves, what he does, well, first of all, a little bit of a background of him. So he grew up in Pasadena, and he loved to repair cars. He didn't really do that. His schooling was okay. He wasn't failing out like Backus, but he wasn't that much into school. But he loved to repair cars. Turns out that's a great background for repairing spacecraft. And so what does he do when he finds that there is this problem with the spacecraft? He tries to duplicate the problem on local hardware. So the Jet Propulsion Laboratory had the very good idea that said, anything we send in space, we should have a replica on Earth that we can now test easily. And so then what he would try to do is he would send, once he figured out the problem, he would send code patches to the spacecraft. Now, in case you don't know what a code patch is a byte-for-byte replacement. So you say, from location 800 to location 1021, just put in this code. Now, this works, kind of, I mean, messages can take 10 minutes to arrive if you're going to, let's say, Mars, but it can work, and that's what he had to do with the Mars lander. So even at the speed of light, things can be a little bit slow. Now, question now is there another approach? And again, if you think about where Reeves is compared to Backus and Rabin, so Reeves says, okay, I have to adapt in real time to a problem, but I'm going to ultimately send commands to a remote computer. It's going to figure out what it has to do. But now, maybe there are other approaches. So the other approaches we would think of is, can the computing element adapt on its own? So is there another approach? When your kid gets older, you expect him to fend for himself or herself. If there's a scrape, get a Band-Aid. So can we ask the spacecraft to do the same thing? And so as the illustrator for the second book that we wrote, Natural Computing, he did this beautiful illustration. So we have a robot trying to fix itself. And the person here is Adrian Stoica. Adrian is also working at the Jet Propulsion Laboratory. He grew up in Moldova, which is much in the news these days, for unfortunate reasons maybe. But anyway, his dream was he always read science fiction, and his dream was to come work at the Jet Propulsion Laboratory. And his idea is to use genetic algorithms to have self-repair on circuits. So just like an older kid who has a bruise, the circuit tries to make itself operational by tweaking its own circuit connections. So you can do this with field programmable gate arrays, for example. But the idea is that there's no human intervention. So if you will, the new human role becomes new age parenting. Try to figure it out yourself. We love you, sweetie, that kind of parenting, rather than you must do it this way. So far he's been able to design circuits that when you introduce a failure, very often they can repair themselves. Now, if we think about what we want to do with that, what we would really like is we would like circuits that repair themselves if possible, but if not, then some other module should take over and be fault tolerant for the whole system. And we'll talk about that a little bit more in a few minutes when we talk about our next inventor. But for now, all I want to do is remind you, and this is maybe not the best slide, maybe you have to enlarge this, but this is just the basic genetic algorithm idea, except that instead of candidates being purely software artifacts, they're now circuit connections. So we have candidate solutions on the top. Over to the right, we allow mutations. We have some notion of fitness. So let's say that your circuit is an amplifier, so a notion of fitness would have to do with amplification. And then there's more. Actually, I can't even read this. But anyway, on the left side, there you evaluate the solutions again, and then you have new candidates. And eventually you get a candidate solution that you hope works well. And what he's able to show is that not only in if there are errors, that very often the field programmable gate array can repair itself. Now mind you, in case you think that genetic algorithms are something that you teach but that aren't used that much, they are used all over engineering. In our book Natural Computing, we talked to somebody named Louis Qualls who designed spacecraft. And he designed spacecraft very much with genetic algorithms. And basically what he does is he takes inputs from all the experts, let's say the expert on shielding, the expert on rocket propulsion, the expert on the payload, and all of them have their inputs, and he uses a genetic algorithm to try to find solutions that are not, that can meet all the constraints while being within some budget. And he finds, interestingly enough, that using genetic algorithms tends to diminish the amount of conflict among people because now the program is coming out with proposed solutions rather than him. And so instead of being thought of as, well, you're just being you're just not liking my design. No, now it's the program that's not liking that particular design. So genetic algorithms are used a lot. In fact, just a few kilometers or a few blocks from me, genetic algorithms are used a lot on Wall Street. So here's Wall Street. You know, even though there's that big thing, really almost all the trading is done elsewhere. And this is Jake and Amrut. And these guys use genetic algorithms to do trading. And without going into too much detail, you could imagine that trading trading these days is very much about short-term trading. You want to predict things in the next little while. And so a typical rule you might want to derive is if the price of a 10-year treasury rises by a certain amount over 2 minutes while the 5-year treasury doesn't move, then maybe the 5-year treasury will move. Well, you want to derive such rules, but there are like lots of such rules. So they calculated that there were going to be 28,000 attributes, and that the number of possible rules would be 1 followed by 28,000 zeros, which is really a lot of rules. So they again use genetic algorithms. The good thing about this application is that even if you don't find all the rules, if you find rules that are good, then that's still fine. You can still trade with that. And so they didn't have time really to think about the actual relationships. They just used genetic algorithms on the past data. And so here's how he describes first going live. I kind of like this. So they turned the algorithm on at 9 a.m. on a Monday morning. System bought and sold $10 million worth of securities in a few minutes. And he said he used to bring 2 shirts to work for the first couple of months because, you know, it's kind of like jumping out of a plane. It's going live and there's all this stuff at stake. So now I want to talk a little bit about how computing and biological concepts are coming together. So one thing that we can observe is that as soon as we get autonomous devices that are solving new problems in new environments, we could easily have accidents. Okay, there's very little control. There used to be lots of mechanical control. And so, for example, early trains, if the power failed to the train, the brakes would simply fall on the wheels. So there would be complete mechanical control that would at least guarantee safety. So nowadays, that's no longer the case. Everything is driven by software, and as we know, software sometimes has bugs. So the consequences could be bad. Now, this problem already existed 100 years ago. If we think about the Titanic, okay, practically speaking, unsinkable. Okay, so this is how the English designers described it. In other words, in practice, it will never sink. That's how it's supposed to be interpreted. But of course, it did sink. Now, they were so optimistic and so perhaps arrogant about their boat that they had no lookouts. The boat was going too fast. There were not enough rafts for the number of people there were. And there was basically no training for mishaps because there were going to be no mishaps. Now, if we look at really in a much more tragic accident, the Bhopal accident in India, where methyl cyanide was released into the atmosphere and poisoned many thousands of people in a nearby village, there were all kinds of problems. The factory was in fact designed well, but the chemical was not refrigerated. It should have been. The refrigerator was out of order. The smokestack scrubbers were out of order, and the population was never told what to do, where all they would have had to do would be to put a wet cloth over their eyes and they would have been okay, or at least more or less okay. But again, just like with the Titanic, no accident would happen. That was the idea, or that was at least the conceit. So this is now the work really of Nancy Leveson at MIT, and her approach is that bad things happen, and that what we need is a notion of feedback. So this is a very biologically inspired idea. And we need feedback and correction. So it's a systems engineering biologically inspired idea. and if we look at the biological analogy, we have skin that heals itself normally. If it's really badly burned, well, if it's on one arm, maybe you can use your other arm. And if both of your arms go horrible as that would be, then other people help out. But the point is that at every level of bad thing, there is some way of dealing with it. It may not be great, of course, but at least there's some way of dealing with it. So her approach is that we have levels of feedback and correction. And what we want to do is we want to make sure that the safety features stay operational. So if we observe the Bhopal situation, really this factory wasn't badly designed. The chemicals should have been refrigerated. There should have been scrubbers. All of that was good. There were even other safety mechanisms that I haven't mentioned. So the design was okay, but there tends to be a degradation of operational safety over time. This is what Nancy Leveson has found in her studies of systems, and and we can see that whenever a terrible accident happens, we see that, well, yes, nothing bad happened when we didn't do this, nothing bad happened when we didn't do that, and so eventually, when enough safety features have been turned off, and there is a little bit of an accident, really, really bad things can happen. So her idea is also very familiar to software designers. We often use some kind of hierarchical design, even if we're also doing rapid prototyping. But still, there's some level of hierarchical design, and so she suggests designing safety right in from the very beginning. So not only what should happen, which is functionality, but what shouldn't happen. So if we think about where we are going with natural computing and where invention is going, we have problems with many unknowns. So unlike the Seiko watch scenario where the environment is very controlled, they often require rapid reaction. There may be enormous search spaces. So for example, if there's a failure, you might have to search a lot of circuit designs to repair it. And that these kind of natural metaphors, and including genetic algorithms, including safety-based design, can apply to many fields from aerospace to design of trading systems. And so much will be happening without human intervention. Now, when I used to give talks about out of their minds, I would sometimes get the question, okay, that was the very beginning of computing, but now computing has been around. How can we possibly invent something cool anymore? And what I think is missed by many people is that as there are confluences of technologies, in this case biology and computing, advances in physics and computing, then all of a sudden there are all kinds of new creative solutions that are required. So even if we think of the computer as an amplifier, let me come back to this. Even if we think of the computer as an amplifier, the computer is not yet a replacement. So even in the case where, let's say, we're using the computer and genetic algorithms to help pick out designs, still those designs have to have been suggested. So and even if we are using the computer to pick out possible numerical values to give to different attributes for trading systems, still those attributes have to have been designed, and or at least conceptualized by people. Now, of course, actually one could debate that because that wall is being pushed farther now with notions of deep learning, where one doesn't need even to say which visual features to look for. But I think there will always be a place where there will be people involved to figure out what are the fundamental elements to be looking for, even if it's just saying a pixel. So now if we look at the inventive styles and see how they've evolved, or not necessarily evolved, but even that they're different. So we have Backus, who's easily angered. We have somebody who likes puzzles, Michael Rabin. We have somebody who loves to repair stuff. We have the encouragement of autonomous computing. especially for environments which are very unpredictable and fast-moving. And we have a whole notion of using nature's notion of feedback to increase safety. So these styles and the sort of techniques and metaphors that these people use are quite different, and I'm sure you will come up with more just on your own, and maybe that will be your style. So with that, I would like to end. With that, what is your style? Okay, and now I'm ready to take questions.
Okay. So thank you, Dennis, for your presentation. It's time now to take a question. We have received a couple of questions from the Q&A space, so let me read a few of them. Let me start with the first one about education. So we have a question which says, thank you for this amazing opportunity. You've gained a big fan. I'm a trainee computing research teacher from London, and the new IT curriculum has a lot more emphasis on programming. The question is, how may I possibly allow my teenagers to develop a new tangent of thinking?
A new tangent?
Yes, I guess a new way of thinking, new find their style, probably. That's my interpretation of the question.
Sure. Well, I think, thank you for the question first, and I really would suggest that if your teenagers are passionate about anything, if it's cricket, for example, because you're from England, then that's fine. Ask them to do some project that involves something that they're passionate about, that involves some level of programming. If they're passionate about doing a visualization, then ask them to even design something by hand first and just do a storyboard. Basically, I find that if I can get my students, especially the ones that I do research with, to find a passion, then they do really well, and to follow their passion. Of course, they need to know certain things, and you usually can determine that. I mean, they should be able to program, of course, in some language. They should understand libraries, especially libraries these days that have to do with machine learning, where many important developments are taking place. So that would be my short answer.
Okay. Thank you, Dennis. So let me take another question. So we have an attendee saying now the perspective is totally different with regard to of not liking school or not. Nowadays, in order to make an invention, it's expected that you have at least a BS degree. Is this because the basic needs are already invented, and so you need a lot of education, more education, in order to come up with some new invention? You need to learn a lot before you can actually propose something?
Well, that's a great question. To me, I think that there are inventions that require a lot of background knowledge, and then there are inventions that just require a new point of view. So right now, for example, I'm working with a high school student who is very interested in neurology, and so I'm asking him to look at synthetic biology, particularly biobricks and related technologies, because one of the things I tell him is, look, it's changing all the time. It's new. And so you're going to be at the forefront of that just as quickly as anybody else. So I think even for somebody without a lot of formal education, if they can either be looking at something in such a unique way, or they can be looking at a field that's changing so fast that they can be at the forefront of it very quickly, I think it's completely possible for them to invent things. Now, this is, of course, I'm a professor, so I'm not to discourage education at all. I think there's a lot that can be invented if one is very well educated as well, but I just don't think it's necessary always.
Okay, great. We have a lot of new questions that are popping up now, so there is a little bit of contention the reception here. Let me take this one. What innovations we expect with special regard to swarm intelligence in real world? which can change the face of innovation in real world via computer science. So I think it's probably collective versus individual invention and collective thinking versus individual thinking. Could you comment on that?
So if I understood this swarm computing, so that is one very excellent technique for solving problems heuristically. I teach a class called heuristic problem solving, and sometimes the students have to compete to solve things, and sometimes swarm computing approaches are the very best. And as in case the listeners don't all know, basically the idea of swarm computing is that you have a lot of not very intelligent agents. You think of them as ants or some kind of insect, and when some ant finds something good, then it leaves a little signal for the other ants to follow. And it's a very adaptive technique, so it could be used also for self-repair. I think it's very exciting. To me, it's something that I haven't yet used successfully. I have used genetic algorithms successfully, but that doesn't mean that it can't be used successfully. I know other people have. The problem with all of these heuristic techniques is that you don't really know if it doesn't come up with a solution, you don't know why. It just hasn't come up with one. And if it comes up with one, you don't even know that that's the best. On the other hand, at least with genetic algorithms, there's this feeling that you're always making progress. The advantage of swarm algorithms is that, especially if the environment is not constant, the swarm algorithms can adapt very well to changes.
Thanks, Denis. We have a couple of questions regarding patents. Let me just phrase one. Do you view patent law as an enabler or inhibitor of creativity and innovation? Other questions are, what do you think of patents? So a couple of questions around patents.
Mm-hmm. Well, I guess I have a few. So I guess I don't think they're totally bad. But certainly some patents have become very troublesome and have stopped innovation. It's a delicate balance in my view. This is more of a policy question than a computer science question, but it's a delicate balance in my view. If there were no patents at all, then everybody would probably try to keep things super secret, and then these ideas would never see the light of day. On the other hand, if patents can be written in such a vague way that they cover everything, and then maybe they can be construed by clever lawyers and their experts in ways that make them apply to some particular very concrete idea that was innovative on itself, well then it's bad. But it's a very delicate balance, and I really don't know what the best policy would be.
Okay, let me take then another question. Do you think computer scientists should understand biology to come up with natural algorithms in the next few decades? I would like to expand that question to, you mentioned the cross-fertilization between different disciplines besides biology. So is this where innovation will come at the crossboard of multiple domains, multiple disciplines?
Well, I think, of course, there's always innovation within every domain. What is really wonderful about biology to me, and one reason I work in it quite a bit, is that they really need us. Because the time when they could use their lab notebook and know everything, or the time when one gene controlled so much that you could say, well, this is P53, and that determines so much. This is why I get the Nobel Prize. Those times may be over. So now it's kind of like a gold rush. The easy gold was found already. So now the new gold is in interactions and in massive data study. So first of all, the biologists need us. So there's a lot of innovation in biology that can be done by computer scientists. Now, the other way I find very interesting also. So this whole feedback notion is really a biophysical biology kind of metaphor that people are using more and more in computing, but even now I don't think not enough. Also, it turns out that even at the genomic level, things are much more complicated than, let's say, genetic algorithms posit. Genetic algorithms basically say, well, there are genes and there are mutations and there can be crossover, and that's about it. But now there's all this all kinds of other mechanisms like RNA interference and jumping genes and all kinds of things. None of that is taken into account in the metaphors that are applied to computer science yet. I have thought about it. I have not yet found any way where they would be really helpful, but that doesn't at all mean that somebody else won't. In fact, I suspect that I'm just missing something important. So I think, reading a kind of general book about genomics and genetic mechanisms, and then thinking about how that might apply to computing, I think that could be a great idea. It hasn't succeeded for me, but again, that's only because I'm limited.
There is a question regarding one of the slides that you did not show, Dennis, which is the Whither Invention slide. One comment is that, can you comment on that actually? Or is that, would you say it's a summary of your talk?
Oh, yeah, sorry, sure. I will be glad to do that. So let me comment on these last two slides, actually. So Whither, the human creative role. So, it used to be that I remember hearing the story, well, computers will never really be able to manage warehouses. It's just much too difficult. It really requires human expertise and human touches. Well, I mean, of course, that's not true, right? So the boundary of what computing can do keeps expanding. To me, this doesn't strike me as necessarily scary because the boundaries of what we want to do also keep expanding. So, if we want to be able to, let's say, figure out very quickly how to repair a wall, it's really great to have virtual reality. Because, now that we have the entire circuit design in our glasses, I mean, that would be so wonderful. So, I think we don't want to think of creativity as always excluding the computer's role. Creativity and the computer are compatible. It's just that creativity will change. Just like nowadays, if you became a chess champion, well, the luster of that is a little, not chess so much, but checkers. The luster of that is a little bit diminished now that checkers is solved. But that doesn't mean that it's not a great game to at least train your kids with. So if you view machines as co-workers and co-inventors, then I think it's a very productive way to do things, and one shouldn't regret that and become atavistic and hope that they go away, because they're just not going away. And it's okay that they're not going away. So in my view, invention in the future will be a lot about modeling the problem and the design framework. So that's really what's happening with the Louis Qualls example, which I didn't review in the slides, but which I mentioned. And also that this problem of safety will become an ever-increasing problem as more and more things become automated. So I think there's a lot of invention that will have to do with that. And of course, there's always a lot of invention that has to do with new technology. So one of the things that is happening now in the wireless world is that people are looking at millimeter waves, so at very high frequency wireless. And that, that introduces all kinds of new problems that are both algorithmic and engineering problems. So anytime there's a new technology, that will require new invention. But the invention will be done in coordination with computers. And also, I think the whole notion of exploration is something that, again, computers can help with, but that people can definitely shape, so that if the search space is too big, you have to figure out some way to reduce it, either through an algorithm or through some a priori constraints.
Okay, Denis, I have a couple of questions regarding what role does age play, if any, with respect to innovation, or what is the can we be an inventor in our early age, or do we have to wait to be old and have gray hair to start proposing new things, given the amount of available results that are available? I think it was also related to one of the questions you already answered. So young people wanting to find the best way or the best path to become an inventor, famous inventor, I guess.
Well, I certainly don't think being older is necessarily an advantage because in some ways one accepts things the way they are more. Whereas when you're young, hopefully you don't, and you might think, can I invent my way around it? So I think actually youth can be a big advantage. In fact, the cliche is just the opposite. The cliche is that one has to be very young to invent. I actually think one can invent at all ages. At least that's what I hope, since I'm no longer that young. And so my hope is that that everyone can contribute. So the way that I've invented, to the extent that I've invented, it's always because I'm easily confused. And so something will come up and I go, well, but I don't get that, and why should it be that way, and maybe it should be some other way. And it's not so much that I'm not quite as angry as Backus, more I guess the style of Rabin, more sort of curious and just seeing how things are. But I think if you have an attitude that is open and where you say, okay, things are the way they are, but it doesn't mean that they have to be. And if you're very interested in something, like who knows? Again, it could be sport, it could be anything. If you're interested enough in something and you think it's wrong, then maybe you just have to ask, well, how would I make it better? And can I make it better by inventing something cool? One more thing I just want to say about that. Sometimes you won't know whether you're going to be a famous inventor based on an invention. So one of the people we interviewed in Out of Their Minds was Don Knuth. And Don Knuth, he's very pragmatic. He says, when I see a problem, I don't necessarily know that it's going to be very important if I solve it. All I know is that I can solve it, maybe nobody else can solve it, and I see the problem right now, so I'm going to solve it. So to some extent, one has to be a little bit unselfish about that. So that is, you might decide to try to invent something just because you think it's cool to do it, and if it's going to have a great impact, great, and you hope it does. But that can't be the only motivation. It has to be sort of the aesthetic of inventing it as well. Just my opinion.
Okay, we have several questions, more philosophical, I would say, or sociological, regarding what people will do when everything will have been automated, or what about jobs for existing people that have been taken away by automation and invention, especially for the current generation. So, I will quote them as philosophical. What is your take on that?
Yeah, well, I mean, of course, it's terrible to lose one's job, especially given that, at least in the United States, it's very hard to get a job when one is even 45 or older. I think that at least in our field of technology, one has to be ready and prepared to be learning all the time. And if you like to do that, then it's a dream field. I love every day that I'm doing things. I just love my job. I love everything about it. But if you think, well, what I would really like to do is I'd like to be in some field where you don't have to learn new things, well, it's really not technology. It's going to be something else. But if you're willing to learn stuff, and even if you're out of a job now, then I think there are things to learn. I mean, for an obscure reason, I put a resume on a job site, not because I was looking for a job, but I did, sort of by accident. And I'm getting inquiries all the time, even though my resume was really, really vague. So I really think that one can learn skills at any age, and maybe the kind of job will change. Maybe it'll be a consultant-style job, but then one can learn skills at any age, and that they can be valuable.
Okay, there is a question about, because you use puzzles, I written that one. I use a lot of puzzles and games in my AI classes, Sudoku, nonograms, etc. They are fun, manageable, and illustrate important points, but we're also trying to remove the perception that AI can't get beyond toy problems. Any thoughts about that?
let's see. I invite the questioner to get in touch with me. I could at least point to some of the puzzles that we do. That some of them are really pure games, but some of them at least suggest practical applications. For example, how to pick up people in a disaster so that as few people as possible die. How to do portfolio optimization for finance. And they're basically all puzzles, and they're framed as puzzles, but they're framed as puzzles that have that are very similar to real problems. So I think it can be done. I think I always loved that aspect of AI, that it had this puzzle feel, and I think sometimes you can just make the puzzles, tweak the puzzles just a little bit to make them look much more relevant to the real world.
Another question, it seems that computer scientist students don't get big picture in education. They are trained for software engineering, not for creative approach to interdisciplinary problems. What do you think on how to, train people better so that we can encourage their creativity? Giving them puzzles.
Well, yeah, that would be basically I would give them puzzles. But I mean, and the reason I would give them puzzles is that at least the puzzles in the class that I teach, that's a puzzle class, it's called heuristic problem solving, is that the puzzles are all NP-hard problems basically, and so there are no fixed algorithms, and therefore people really have to use their creativity. Now, mind you, of course, it's really good when students can program well. If students can't program well by the time they hit that class, then it's really not, they can't really do the class. So there's certainly a level of skills that one needs to learn. I don't think I think there's still room for a course or two that explores creativity. So yeah, I think it's a balance between the two.
Okay, another teaching-related question. What is, in your opinion, the best way to learn any computer language?
Oh, interesting. So the way I learn computer languages is the way I learn natural languages, which is that I look at examples, worked examples, then I cover them, or at least don't look at them, and then try to do it myself. Okay, now at the beginning, of course, I might try to do it more or less verbatim, or at least to just make sure I'm using the constructs that they use. But afterwards, I might do it in a completely different way. But the point is that if you have a worked example where you know what the correct solution is, then it's not so hard to correct yourself, to correct little bugs at least.
Okay, there is a question regarding your presentation on Backus and FORTRAN. I'm working with NOAA and NASA on climate modeling software. The criticism that Backus had of FORTRAN are still blocking us today. Do you ever see functional programming going mainstream? More generally, how do we break away from the old ways on huge projects?
Okay, well, this is great. This would allow me to do a long rant, but I think we're almost at the end, so I won't do a long rant. I think even if we don't have pure functional languages, we can have languages that are at least partly functional. So in one of the Backus slides, I give an example of a language that I use, which is a descendant of APL, and that language, although it doesn't use the APL funny character set, is functional very much, except there's also assignment. But the point is that each construct is so powerful that that one doesn't need much code, and because one doesn't need much code, it's much easier to inspect and understand what's going on and change. Now, of course, this might not be available to every application. Some applications really require very low-level code. So, for example, Glenn Reeves would have to, has to understand the machine language to do patches. But for many, many applications, the higher level one can be, whether it's R or MATLAB or Julia or this language that I use, Q, then it can be very productive to try a higher level approach. Also, I think ultimately those higher level languages will be faster because they'll make better use of multi-core.
Denis, maybe I have two final questions. What do you think about the new opportunities of collaborative invention because of the new connectivity of people around the world?
Well, I love the idea. I think that in my experience, it's always been helpful to be in the same room, at least at the beginning of the invention. The end can be done remotely, but there's something about, maybe Skype can be enough, or something like Google Hangout or whatever can be enough, but you sort of have to, in my experience, to work with somebody well, it really helps to know them well, even outside the question you're asking. To take walks with them, to talk about other things, to eat meals with them, whatever. Again, this might be me. It might just be very specific to personality. But so in my opinion, I think it's the very beginning of an invention really requires close proximity, but maybe afterwards not so much.
Maybe a final question. I'm sorry, we have so many questions. We can't go through all of them. Your example showed people come from so many different backgrounds, personalities, and mindset. Is it futile to foster inventiveness within large organizations through a systematic process?
Sorry, what was the last part? Is
it futile to foster inventiveness within large organizations through a systematic process?
I see. Really, I don't know. No. First, I hope it's not futile, because we depend on those large organizations. And if you think about Google, it's pretty large, yet they're inventing stuff all the time. There are a lot of companies that are inventing things all the time. So I think it's hard to get such a culture, but I really have no expertise in large culture management or anything like that.
Okay. So I think we are about the end of our time. Thanks a lot, Denis, for the presentation and taking all these questions. Thanks for all the attendees for attending this webinar. And I wish you good journey and in the world of invention. And I hope that this talk will have been a source of inspiration for all of you. Take care, and thanks again for joining us.
And a personal thanks from me. Thank you so much.